Alright, so on Tuesday we talked about the differences between an electrolytic cell and a galvanic cell, and we saw that based on an electrolytic cell there were a couple of differences. The first difference was the fact that the galvanic cell takes place in 2 cells and the electrolytic cell can take place in 1. The next difference is that we have to have a power supply to force the electrons to go in the direction of the anode, from the anode to the cathode. And then the last difference was the fact that the anode had a positive charge to it and the cathode had a negative charge to it. So those are our 2 differences between an electrolytic and a galvanic cell. So let's talk about how we can use this. Well, here's the differences, and here's our mnemonics. These still work. Reduction takes place at the cathode. Oxidation takes place at the anode. The flow of the electrons is from the anode to the cathode, just like we did before. The only difference is the fact that we have, in an electrolytic cell, a positive anode. That's the only difference. So, how do you predict the products of electrolysis? Well, it depends on what you are putting in your cell. There's 2 different kinds of cells. There's a cell with no water, which means it has a molten salt. And if that's the case, it's just anything that is a salt. So it would be something like a cell that has molten sodium chloride. And if that's the case, then the cation is being reduced. Oops. Sorry about that. And the anion is the one being oxidized. So, in this case, we know that the sodium ion, because sodium is an ion when it is in sodium chloride, that the sodium ion is going to be reduced. So how is it going to be reduced? Well, you're going to add electrons, 1 of them, and what are we going to make? We're going to make sodium solid. And this is the reduction reaction, and it's exactly what's on your reduction potential table. Now here's where it gets tricky. The anion is going to be oxidized. So what's our anion? Well, in this case, it is chloride ions. Okay? And when you go to look for chloride ions on your reduction potential table, you will have a hard time finding these because they're actually on the product side. This is the oxidation reaction, so you're going to have to flip it. So it would be 2 chlorides yields chlorine gas and 2 electrons. That's the reaction that you'll find on the reduction potential table, just flipped as the reduction reaction. We want it to be the oxidation reaction, so we just flip it. So if it's a molten salt, the metal is going to be reduced, and the nonmetal, the anion, is going to be oxidized. And you can just calculate the E of the cell based on that. If there is water present, we've got a couple of rules we're going to have to follow. So instead of being, say, liquid sodium chloride, as it would be if it were molten salt, let's say instead it's aqueous sodium chloride. Well, think about what's in our beaker. If it's aqueous sodium chloride, there's some stuff in our beaker. In our beaker, we're going to have some sodium ions, some chlorine ions, but we're also going to have some water molecules. And water's on your reduction potential table, we just haven't used it very much. So grab your reduction potential tables and let's find water. Water is in 2 spots on your reduction potential table. What I'd like for you to do is take out a highlighter or something, or a pencil, so you can circle these 2 reactions for water on the reduction potential table. If you look at the top, there is a reaction that has water. It's at positive 1.23. Go ahead and highlight that reaction. Alright, that's the reaction where water is a product. Now go down a little bit further on your reduction potential table. If you go down to negative 0.83, you find another reaction for water. And in this one, water is a reactant. So circle or highlight those two reactions, and it might be a good idea to circle or underline the water and show that the water in one of those reactions is a product, and in the other reaction it is a reactant. The top reaction is the reaction you would use if water is oxidized. Because you flip it, it becomes an oxidation reaction. Water is oxidized in that reaction. The bottom one is a reduction reaction, and water is a reactant. Therefore, that's the reduction of water. So we're going to use those two, and we're going to play with them, and sometimes you have to use them to see what's going on. So it tells you, in our rules, it says, use the reduction potential table to see if water or the ions are reacting. Now here's a couple of rules. Group 1A and 2A metals will not be reduced in an aqueous solution. Now why is that? Well, look at the reduction potential table. If you had water and you had sodium ions, so we have sodium or water, which one's going to be more likely to be reduced? Is it going to be the sodium ions or is it going to be the water ions? Well, the water ions have a more positive reduction potential, therefore the water molecules are the ones that are going to be reduced. If you look at all the reactions beneath that water reaction, the one that's at negative 0.83, all of those metals are group 1 or group 2 metals, with the exception of aluminum. Okay? Everything else is a group 1 or a group 2. So water has a more positive reduction potential than all of those metals, which means water is more likely to be reduced in that case. If it's not a group 1 or a group 2 and it's above water, well then it's going to be the metal that's going to be reduced. Then the second part of this says, no polyatomic ions will be oxidized in an aqueous solution. Water will be oxidized. So if we had a polyatomic ion in here, then it's going to be the water that's going to be oxidized. If we don't have a polyatomic ion in there, sometimes we have to look at what's going to happen. If all else fails and you don't know what to do, oxidize your water. All right? So let's look at a couple of reactions or a couple of electrolytic cells and figure out what's going to happen in those two, with these two types of ions. So in the first one, I have a question of sodium. Oops, let me go back. Okay, so I have either sodium ions or water ions. That's what I've got to find out first. Is it going to be the sodium that's reduced or the water that's the reduced? Well, water has a more positive reduction potential than sodium does, and sodium's a group 1, so in this case it's going to be the water that's going to be reduced. So we're going to pick the water reaction, so we're going to write 2 H2O's plus 2 electrons yields hydrogen gas and 2 OH minuses. Alright, so it was the water that was reduced. What's the reduction potential of that? Well, it's straight off the sheet. It's negative 0.83. So now the next question is, well, is it the chlorine ion or water that's going to be oxidized? And in this reaction, it's going to be the chlorine ion. Usually, if you have a monatomic anion, it's the monatomic anion that's going to be oxidized. So let's look at that reaction. That reaction would be 2Cl minus yields Cl2 plus 2 electrons. And it has an oxidation potential of negative 1.36. So now I can write my balanced redox reaction. It's 2 waters plus 2 chlorine ions yields hydrogen gas plus 2 OH minus plus Cl2. And the E of this cell would be equal to negative 0.83 plus negative 1.36, which is negative 2.19. So, in that reaction with molten sodium chloride, the water is reduced, the chlorine is oxidized, and we get an E of the cell of negative 2.16. Is this a spontaneous reaction? The answer is no. Because E is negative, delta G would be positive, and that's the sign of a non-spontaneous reaction. All right, let's move to the next one. We have nickel and we have sulfate. So, we'll just change colors for the next one. So we're going to say, the question is going to be, is it the nickel or the water that's going to be reduced? Well, you go and you look at the reduction potential tables, and you find that nickel has a more positive reduction potential. Therefore, the nickel, in this case, is going to be the one that is going to be reduced. So it's going to be nickel 2 plus 2 electrons is going to yield nickel solid. And the reduction potential for that is negative 0.25. Now we're going to look at the anion. Well, is it going to be the sulfate or the water? Well, I just told you that polyatomic anions are never oxidized. Why? Well, that's just the way it is, and they're not even on your reduction potential table, so you can't find them anyway. So if that's the case, then it has to be the water. So the water is going to be oxidized. Why does the water have to be oxidized? Well, we already know the nickel rigged. So the other thing has to oxidize. So we're going to go find the oxidation reaction for water, which is the top one. The top one is the only one that you can flip and make water a reactant. So it's going to be water, 2 of them, yields, and we get O2 plus 4H plus 4 electrons. And this has an oxidation potential of negative 1.23. So now we can write our balanced redox reaction. We have to remember to balance for electrons because this one has 4 and this one has 2. So we're going to multiply this one by 2. And we can write our balanced reaction to be 2 nickel ions plus 2 waters yields 2 nickel atoms plus oxygen plus 4 hydrogen ions. And what's the E of this cell going to be? The E of the cell is going to equal negative 1.48. 1.48. Alright, let's look at the very last one. We've got sodium and sulfate. So what's more likely to be reduced? The sodium ions or the water? Well, we know sodium's a group 1. It's never going to be reduced because it has a lower reduction potential than the water. So in this case, the water is going to rig. Alright, what about my anion? Is it going to be the sulfate or is it going to be the water? Well, we already said that polyatomic anions don't oxidize, so in this case it's going to be the water that oils. So in this reaction, what's really happening? The water is going to reduce and the water is going to oxidize. So the reduction reaction of water and the oxidation of reaction of water are two completely different things, and we got to keep that in mind. 2 waters plus 2 electrons yields hydrogen and 2 hydroxides. That's the reduction reaction for water. The oxidation reaction for water is 2 waters yields oxygen plus 4 hydroxides plus 4 electrons. Alright, so let's look at the exchange of our electrons. We've got 4, we've got 2, so we've got to multiply this up here by 2. And so that gives me 4 waters and 2 waters, which is 6 waters. Gives me 2 hydrogens plus 4 hydroxides plus oxygen plus 4 hydrogen ions. Well, here's a little problem. Alright, here we have hydroxide and hydrogen. And so what's that going to do? Well, those two things are going to come together and form a water. We're going to get 4 waters over here. I have 6 waters over here, so that's going to end up with a net of 2 waters. And that's going to yield 2 hydrogens plus oxygen. And this reaction is called the hydrolysis of water. We are making the elements, hydrogen and oxygen. Alright, that's the most difficult part of all of this. So, let's go to the next slide. The next slide is about calculating and doing all the calculations. We had some practice with that with the pre-lab, but let's walk through how to do this with the calculations. And we're going to go through 2 examples to help you prepare you for your homework. Alright, so here's 2 things that you can calculate. First, you can calculate how much of a metal could be plated out. That's the first thing. And that means grams. How many grams of a metal would be plated out? You can calculate that. And then the second thing is how long would it take to plate out a specific amount, which means time. So your questions are either going to involve how much did you plate out, or if I plate out this much, how long is it going to take to do it? And all of these equations are based on this, which is the Faraday's law. The amount of a substance being oxidized or reduced at each electrode during electrolysis is directly proportional to the amount of electricity that passes through the cell over a given amount of time. So Q is equal to I times T. We've already used this. Remember, Q is coulombs, I is amps, which is coulombs per second, T is time, which is in seconds, and remember we have this Faraday's constant. So here's the steps. If we have current and time, we can convert that to coulombs. And then if we know coulombs, we can go to moles of electrons using Faraday's constant. If we know moles of electrons, we can get moles of substance. Now that we're going to use the reaction, alright, and use molar ratios of electrons to atoms. And then if we know moles of the substance, we can convert it to grams of the substance by using molar mass. So let's walk through a couple of examples and make sure you guys are doing okay with this. So the first practice problem deals with aluminum and aluminum chloride, molten aluminum chloride. So in this case, we're asking about aluminum. So we know the aluminum is going to start out as an aluminum ion. It's aluminum 3 plus 3 electrons yields aluminum. Because if it's molten, then that's the cation and it has to be reduced. So we are starting with, first we need to find coulombs. What do we know? We know the amps, we know I, it was 10 amps or coulombs per second, and we know the time. The time was 1 hour. Well, that has to be in seconds, so let's convert that to seconds. There's 60 minutes in an hour and 60 seconds in a minute, so 1 hour has 3,600 seconds. So let's calculate the coulombs. Coulombs is equal to I times T. And so my I is 10 coulombs per second. And my time, and so when I calculate that, I get 36,000 coulombs. So now I'm just going to go through the process. Alright, the steps are coulombs to moles of electrons. Moles of electrons to moles of aluminum. Moles of aluminum to grams of aluminum. So let's start. I have 36,000 coulombs, and I know for every 96,500 coulombs, that's 1 mole of electrons. Alright, coulombs cancel out, and now I'm in moles of electrons. The next step is to go to moles of aluminum. Well, I know for every 3 electrons, or 3 moles of electrons, I get 1 mole of aluminum. 3 moles of electrons for every 1 mole of aluminum. Moles of electrons cancel out, and I'm left in moles of aluminum. And now I just need to go to grams, and for every 1 mole of aluminum, there are 26.98 grams of aluminum. Where did I get that number? It came from the periodic table. That's the molar mass of aluminum. So we grab our handy dandy calculator and we do some calculating, and we get an answer of 3.355 something 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 grams of aluminum. With sig figs, it needs to be 3.36 grams of aluminum. How do I know it needs 3 sig figs? Well, we had 3 sig figs here and 3 sig figs here, so my answer needs to have 3 sig figs. Alright, so we just went through these steps. Coulombs to moles of electrons to moles of aluminum to grams of aluminum. Just going through the calculations. So I'm going to go ahead and give you guys the next problem, and I want you to see if you guys can work it out. So let me give you the next problem. Alright, the next problem is about magnesium chloride, molten magnesium chloride. So we know that the magnesium is going to be reduced, and there's the reduction reaction. So I want you to calculate the mass of magnesium formed when you use 60 amps for a period of 4 times 10 to the 3 seconds, or 400 seconds. So let's stop the recording and give you guys a couple of minutes to calculate that, and then we can play the recording again and I can show you the answer. Alright, so we know our amps are, whoops, let me get back. Okay, got a pen now. So, we know our amps are 60 amps, and we're going to go for 400 seconds. So, our coulombs are equal to 60 coulombs per second times 400 seconds, which gives me a total of, it's 4,000 seconds, I'm sorry. 240,000 coulombs. Now we got to get to grams of magnesium. So we're just going to start. Faraday's constant. That many coulombs in a mole. We know for every 2 moles of electrons, we get 1 mole of magnesium. And then we know 1 mole of magnesium is 24.31 grams. And so you go through and you do all the math, and you get 30.2 grams of magnesium. We need 2 sig figs because our numbers both had 2 sig figs. Alright, we can stop the recording and you guys can see if you can do the second problem. And this time we're starting in grams and we want to find the time. So we're essentially doing the same thing, but we're going backwards. So take a few minutes and let's see if you guys can work through that one. Alright, let's do the second one. So we're starting with 50 grams of magnesium, and we want to know how long is it going to take to plate out that much magnesium when the current is 100 amps. So we got to go backwards and we got to get to coulombs. So we know that there are 24.31 grams in a mole of magnesium. And we know for every 1 mole of magnesium, we have 2 electrons, 2 moles of electrons. And we know for every 1 mole of electrons, there are 96500 coulombs. And so we do all this math, and we find out we have 396,955.9852 coulombs. Alright, so we're going to go back to Q equals IT, but we're going to rearrange it because we're trying to find time. And if Q is equal to IT, well then if you rearrange it, T is equal to Q over I. So now you just plug things in and make sure your units are the same. So we have 396,955.9852 coulombs in 100 amps, which is coulombs per second. Coulombs cancel out, and I'm left with 1 over seconds, which is seconds, and so that is 396.9 seconds. And technically we need 3 sig figs, so in 3 sig figs that would be 3970 seconds. So I hope that helps you guys to figure these questions out. You have a UT homework assignment that you're going to have to do for this unit, and these notes and this video should help you guys be able to do those problems. Good luck!